over the synthesis of capnellene. And capnellene was derived from the coral. It looks kind of like this. I drew it out. The coral called Capnella, also known as the Kenya tree coral. Now, capnellene specifically is a naturally occurring compound in this coral. And what was very intriguing about the naturally occurring compound is first its shape. It has a tricyclic shape, so a lot of chemists were in the lab trying to produce the tricyclic shape from compounds that only had one cycle, and they were trying to build off of that cycle and carbonyl group, which is what the article I did today is based off of. And it was also intriguing in a medicinal sense because it was found to have antimicrobial and anti-inflammatory properties. So now research has been more geared toward how helpful the synthetic version of the capnellene derivative is that was gathered from the coral. So just researching about the synthetic one versus the naturally occurring one and seeing if the properties are the same, even though it was synthesized in the lab versus in nature. So the researchers today that my article went on about are Leo Paquette and Kenneth Stevens. So they published the article called Stereo Controlled Total Synthesis of the Triquinane Marine Sequesterpine. And the other thing is that capnellene originally, or like now as well, it's known as this. This is actually the structure name, the compound name, but people commonly just erase this part out of it, and that's why a more common term is just the capnellene. So to start the synthesis off, similar to what I was mentioning previously, what they did was started with a cycle, and their chosen cycle was a cyclopentane, and it has a dimethyl there, and it also they attached an aldehyde onto the carbon. I'll number it onto the first carbon, and then the dimethyls are onto the second carbon. So from here, they used a phenyl magnesium bromide. Let me write that out. Phenyl magnesium bromide. And in their article, they have it as on the same process, but I'm going to draw it out into two steps to kind of give the background. And this phenyl magnesium bromide, or the magnesium bromide itself, is commonly seen and known to be a part of the Grignard. They're Grignard reagents, or you can hear it as a Grignard reaction, which this is a Grignard reaction. So chemists normally see whenever a compound is paired with this magnesium bromide, they, in their mind, think of a carbanion. So in actuality, we have a carbanion that is readily available to attack this carbonyl group. And when it attacks the carbonyl group, right here on the center carbon for the aldehyde, the carbon oxygen pi bond is going to break and push those electrons onto the oxygen itself. So what we're going to see is a new compound, or a new structure, I should say, that includes the carbons that we just added, and it also puts the negative charge on the oxygen, since we pushed and broke the pi bond there and pushed the electrons onto it. So now this oxygen has more electrons than it once, making it have the minus charge. So what the researchers noticed when they were doing this is that a condensation they induced a condensation mixing with whenever it was mixed with the vinyl magnesium bromide. So I'm gonna assume, since they said that, I'm gonna put that there was water in the mixture. And this water is helpful because it allows the oxygen to protonate itself and create an alcohol. So we're going to, our new structure is going to look like this. Oh, and we just added this hydrogen on here. So we just created an alcohol. Now, for this molecule is stable. However, you can't really do too much with it unless you kick this structure out, changing it to a leaving group or attacking it with something else. So something that's a little bit easier to do is just to switch it to a ketone, because carbonyls or carbanions are gonna love to go attack the ketone, which is gonna be seen later on in the synthesis. So in order to do that, we're gonna oxidize it, and what they used is manganese dioxide. And what they saw was this reaction, that the reaction itself occurred very smoothly. And all it does was change our alcohol group back to a carbonyl group that we had, not the same carbonyl group. Now we have a ketone carbonyl group. So this pi bond right here is formed again. And this step is oxidation. So it's oxidation reaction. Now, what they noticed was in doing so that they didn't have any problems with this, that it was a smooth reaction. It just easily produced this product. Another thing back here, when dealing with the Grignard reagent, to collect the product here that has the alcohol group, they used high pressure, they used a high pressure liquid, or I don't believe it was liquid. I don't think they specified. They did specify, It was a high pressure liquid chromatography. That's how they collected this compound. And then they did the oxidation reaction using the manganese dioxide, and it produced the compound with the ketone. So from here, we're going to do what is known as a Nazarov cyclization. So this works with divinyl ketones, which is what we have. We have our 2 carbons here, so that's 1. Then we have this other one, so it's di, and then we have our ketone in the center. And the reagents used here, or what they used specifically, was an 8% phosphorus pentoxide, and they also used methane sulfonic acid. So this itself, they put this compound here very quickly into this into the reagents. So it was set at around 20 degrees Celsius, and it was left for about 2 minutes. And from there, the product was collected. But the background mechanism behind it is that we essentially, I'm just going to put A to represent the acid. So essentially, we're going to have I'm going to redraw it here to make it look visually a little bit more understandable. We have our oxygen that has its electrons, and we have our A group. And for this, it's normally the oxygen grabbing a Lewis acid. So I'll put La, and we're gonna pick this up. So what we're gonna do is pick this up, which in turn breaks this pi bond, and we're gonna just break that, and it's gonna move onto the carbon, the charge. So from here, we're going to have a structure that has a carbocation, and we just attached this to our oxygen. right there, and our carbocation goes here. Now, this carbon is in a very bad position because, one, it's already electron deficient. It's saying right here, this positive is telling us it needs carbons. And the other reason is because it's by this highly electronegative oxygen atom. So it's kind of just like way too much of a electron deficiency going on in here. So to help that, what we're going to do is break these pi bonds. We're going to break these pi bonds here, push this pi bond to break here, and it will fulfill the carbocation that is deficient, electron deficient right now. It'll fulfill that. So the structure is going to look like this. We broke that, and we now are creating our cycle, our other cycle, because as I stated previously, this is a tricyclic, or this compound has a tricyclic shape. So it'll look like that, and this stayed the same. We haven't changed anything here, but we did, since we broke the pi bond here, our carbocation now moved to this carbon, which it still is electron deficient, but it's a little bit better because it's not directly attached to the oxygen atom. However, we still are going to help the carbon to make a stable compound. So here we're doing a beta. This is the alpha position, and excuse me, this is the alpha position, and this is the beta position. So we're doing a beta hydrogen elimination, which is essentially just gonna move this. We're gonna take this hydrogen, and it's gonna break this pi bond and allow it to form a new pi bond that will stabilize the carbocation right here. So the compound, or our structure, our new structure, is going to look like this. Boom, 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 boom. And then we still we haven't messed with the oxygen just yet. And we have our pi bond from the last time, and we formed our new one right here. So from here, we're gonna what we're gonna do is, now we have so this hydrogen was taken, it's now in the environment. So we have this H plus here. This pi bond is gonna break to satisfy, to go get the H plus. So first, the oxygen bonded to the Lewis acid is gonna break. That bond is gonna break, and it's gonna push it here, which in turn is gonna break this carbon-carbon pi bond and go and pick up a hydrogen, which results in our structure to look like this for now. So we removed that double bond and we produced a ketone here, and then we have our hydrogen that we picked up there. So whenever they were doing this part, as I mentioned previously, it was only in the 8% phosphorus pentoxide and the methane sulfonic acid solution for roughly 2 minutes. But they did find that when doing it this way, they got a 62% yield. So that was really good. So for this product right here, they got a 62% yield, and basically the product in this synthesis, in short, is just a Nazarov cyclization, which is just the acid catalyzed ring closure of the divinyl ketone that we had. Now, using this compound that we made from here, the synthesis will continue. So I'm going to just paste this over here really quickly. And what they did next involves Michael addition. I'm going to erase that because we don't need that anymore. The hydrogen is there. So we're using cuprate reagent, which is basically to make this reagent that I'm drawing right now. We combined an organo copper and organo lithium together, and they also had it in a solvent, and the solvent was the ether. So this right here is gonna do a Michael addition to the pi bond here. So what's gonna happen essentially is a way that you can see it a little bit easier is saying that the carbon has a minus charge on it. That's gonna go and attack this position right here, which is gonna then break this pi bond and push the charge onto this carbon right here, which results in the structure to look, which results in the structure that looks like this. Boom, boom, boom. And we were able to add that methyl group right here. And we have a carbanion here. And again, there was some water in the solution. So I'm going to this carbanion is gonna pick up this hydrogen from the water, and it's gonna result in this stable compound that is gonna be used for the next part of the synthesis. So now we have our molecule that looks like this. Now the next part of the synthesis is mainly just to attack the ketone. But before I do that, the reason that they did it this way that I'm going to talk about in a little bit is because these next few steps, so they were successful in making this compound right here. And for time, I'm just going to write them and talk about them, which in turn made this compound. They were able to make this compound, produced an aldehyde. And then they used Greenyard to do this. And so the way that I'm doing it, the reason why I'm writing them really quickly here is because this wasn't successful, but I did want to go over it because this is the reason that they chose to go the other route. So our last step here, it looked like this, and it kind of attached, or it was trying to make the other cycle. And it kind of just had like this positive charge throughout here. And their goal of this was to the goal of this was to create this, which they would use to get to the desired product. So from here, this step worked. This was adding the copper lithium reagent as in a Michael addition way. So from going from this ketone to the, this should be a 3 right here, to the silicone triamine, what they used was tris, and then as well as the butyllithium and TMDA and this trimethyl silicone chloride, and this produced this compound that has the silicone triamine on it. And from here they successfully used Friedel Crafts. So they had chlorine, CH, right here, and then we have an AlCl3, which essentially is a carbocation. So they allowed these right here. They used these as the reagents, and it ended up attaching the the aldehyde here onto the compound, which is good because that allows for to get a step closer to cyclizing, and from here, what was used to go from the aldehyde to the ketone that we see here, it was similar to previously mentioned a Grignard reagent. So there was a Grignard reaction, and then they it's a two-step process. So they did Grignard first, and then they did an oxidation, and that made this ketone here. They hydrogenated it, and it produced an alcohol with these plus just kind of going through everything. And now this step is where it messed up. They realized that this wouldn't actually happen, so this kind of stopped them right here. This is where they realized it didn't work, but their goal was to go from use this to get to here and then be able to get to the desired product. To create the desired product, they discovered a new route to do, which still use this product. They just didn't go through all these steps. They used that product, or this product right here, and what happened here is kind of a similar idea with trying to do or use a carbanion. So here it looks kind of like this, and we have this carbanion structure that you can kind of see it to make it a little bit easier. It just readily attacks this carbonyl group, and it breaks the carbon-oxygen pi bonds and forms the molecule that looks like this. O minus, and we just added these on here. So we just added the two carbons, so carbon 1, carbon 2, and then the oxygen now has a minus charge on it, and the oxygen is gonna get protonated and turn into an alcohol. So it's gonna look like that. We formed an alcohol, and we have this product. So from here, what they decided to do was place it in a very acidic environment, and these are the reagents that they used. So they placed it into a very acidic environment. They used formic acid containing sulfuric acid, and what they did was place this in a put the temperature to 90 degrees Celsius, and what it did was induce a Roop rearrangement. And basically a Roop rearrangement, they found that this method was highly effective, and it reacted very smoothly. So since this is an acidic solution, I'm just going to write that we have it's a lot of H's in here. So what the alcohol is going to do, the oxygen specifically, is going to pick up a H that's in the environment, and it's going to produce water. So the addition of the H to the alcohol creates water. So now we have this H2O group, and the O has a plus charge on it, which water is the leaving group, so it's going to then leave the structure, and we have a new compound or structure that looks like this, and it created a carbocation. So the carbocation that is formed is going to be stabilized by removing this hydrogen. So the water that left here is now in the system. It's going to act as a base, and it's going to take this hydrogen, breaking this bond and forming a pi bond here. So what we have is a compound that looks like this. And then we have our pi bond here, and we have that right there. So from here, we ended up doing... So from here, we have this triple bond, and we have this... I'm going to put a CH here, and then this is a carbon right here as well. We have this H3O plus in our system. This pi bond is going to break, and removing the hydrogen, it's going to remove this hydrogen from the H3O plus, and it's going to produce water, and then this pi bond broke, and now it's going to be added to the carbon here. The hydrogen is going to be added to that carbon. So it's going to be like this. Carbon, boom, boom, carbon, and this has H2. And right here, what we did was, so from here, excuse me, I'm just gonna, why is that? Okay, we have this right here. I'm gonna just rewrite it. Okay, sorry. So from here, it produced water as a byproduct, or just as a result of removing the hydrogen. So the water that was produced is now going to OH. We also produced a carbocation since we broke the triple bond. So this water is going to go help out the carbon and be attached directly onto the carbon. So we're going to have something like this. Carbon, boom, boom, CH2. Don't forget we have a methyl here. And ROH. And then we have a plus right here. So what's going to happen is water that's in the system is going to take a hydrogen atom from this part of the structure. So this is the oxygen is going to remove this hydrogen, and it's going to break the oxygen-hydrogen bond and push the electrons towards the oxygen, and that produces a structure that looks like this. We have our carbon connection, and our carbon is still connected to our oxygen, but instead of it being connected to water, it's just to alcohol now. And a keno-eno tautomerization is going to occur, and it's going to produce, so this right here is keto-eno tautomerization, and then this whole thing, well, this part to this part was the group arrangement. So group arrangement. Okay, so I put group just so that it's identified. Group rearrangement. Okay, now a keto-eno tautomerization is going to occur, and it's going to look like this. We're going to have, Why did that do that? We're going to have our ketone here. Oh, okay. And from here, what happens is similar to what happened previously. We're using a Grignard reagent, CH2, CH. So it's just vinyl magnesium bromide, copper iodide, and they use tetrahydrofuran. And the temperature for this was negative 78 degrees Celsius. So this was negative 78 degrees Celsius. And since I did a reaction similar to this, I'm just going to show the product. It added in a micronization way. Just remember that this was, this can also be seen, or it is also seen as a carbanion. So this added in a microaddition way to the to this structure right here, and in doing so it produced, let me draw it out, we still have our ketone and we still have our methyl group here, but we're adding this structure. So it's gonna look like this. And from here, ozonolysis is going to occur. So what they used for ozonolysis was this CH. So, and then CH3. Okay. Now here, what happens in short is basically this carbon-carbon bond is going to become aldehyde. So I'm just going to write a smaller way to do it with the R group, but just being that our R group is the structure itself. So a simpler way to look at it is that our R group here, which is the structure, in this, oops, I meant to put that, yeah. This alkene is right there. So what happens is we have our O3, which is an oxygen that has a minus and one has a plus. So what happens is essentially kind of like a chain reaction. So the pi bond breaks and attaches to this oxygen, which breaks this oxygen-oxygen pi bond, pushing the electrons onto the center oxygen, which in turn pushes this to go here. Excuse me. Pushes this to go here. So it's kind of like a chain reaction. The oxygen connects to this carbon, breaking this pi bond, and then breaking the oxygen-oxygen pi bond, producing a structure that looks like this. O, O, O. Then we have our carbon here, and our carbon has our hydrogen. So here what happens is kind of another chain reaction. This is going to break onto this carbon, and this is the structure that we're going to want. This part here breaks on to here. And from this is going to break here, which is going to produce push these electrons onto here. So what we're making is our aldehyde, and it's also a byproduct is this carbon connected to the oxygen. So right here it would look like this. However, we still have that O minus, but this is the product that we are looking for. And this R group again is the structure. So what the actual compound product looks like, following the same mechanism, just replacing the R group with our structure, it looks like this. We still have our ketone here, and we are just replacing it with the aldehyde. So this, oh, excuse me, sorry. This is this part. This is this part. And this is the R group. Okay, now from here, what happens is an aldol type reaction. So I'm just going to redraw the structure. Oops. Okay, and what they used is potassium hydroxide as a base. They specifically did 5% potassium hydroxide in a 2-to-1 mix of the tetrahydrofuran and ether. So here what happens is the hydroxide ion is going to remove a hydrogen from here, breaking this bond, pushing it here, which is going to break the carbon-oxygen pi bond and produce a structure like this. I'll do it down. And this oxygen is here with the minus on it, and it's connected to, it's not double bondly connected to the carbon that has its hydrogen still, and we have our aldehyde here, H. So what happens is this oxygen with the negative charge is going to use its electrons. It's going to push down here, breaking this pi bond and connecting it straight across to the carbon on the aldehyde, which in turn breaks the carbon-oxygen pi bond. So the resulting structure is going to look like similar to this. Then we have our oxygen here. We have that there. And we have our O minus here. O minus. So what's going to happen is, again, I'm not sure if I mentioned it. This is the aldol type reaction. So what's going to happen is we have water in the mixture. The oxygen is going to grab a hydrogen from the water and become an alcohol group. So it's now going to look like this. Alcohol group here. And the alpha carbon from, which is right here, a hydrogen is going to get removed from there. Since we made this OH ion in the previous step, it's going to remove a hydrogen from here, breaking this bond and moving it like that. So we're going to produce our structure that looks like this. Double bond, and we have our O minus here. Okay, now what's gonna happen here is we're gonna push this here, push this down, and kick the OH group out. So now it looks like this compound right here. We still have our methyl group there. We just formed a ketone, and we also made this double bond right there. Now from here, what was done was just hydrogenation. So it was just a H2. We just put H2 in it. What do we call H and methanol? Okay, and methanol, and all that does is just it's gonna remove the alkene that's right there. So we're just gonna have cycles of just alkanes, and our ketones still there. Acidic, so we're gonna have our just gonna redraw what we have with our methyl here and our ketone there. So this is gonna be Vidig. We're gonna have this reagent, and it also can be seen as this, a carbanion, which is going to attack this ketone right here and break the pi bond there, and our structure is going to look like this. We have our O, and then we have our CH2, excuse me, I don't know why I put a 3 there, 2, and our other group right here. And now this oxygen has a minus on it. It's going to go and attach here, and it's going to cyclize. And it's going to cyclize to make a structure like this. O, CH2. And basically what's going to happen is that it's going to kind of go like this. And we're going to get our desired product of the capnellene. So it's going to look like this. Then we have our, we have our double bond that we just formed from this step using Vidig. And this is how the final structure will look. So they were able to synthesize it, and they found that while it did work, the overall yield was very low. It was only 8.3% yield of the actual desired product. So it was pretty low. But that is the synthesis of capnellene. Thank you.